Good morning to all. So now we discuss equivalence relation. Okay. So in equivalence relation, so what is mean by equivalence relation? That is, a relation capital R on set capital A is said to be in equivalence relation if it is reflexive, symmetric, and transitive. That is, the given relation will be satisfied the three properties, that is called reflexive, symmetric, transitive. Then it is called as an equivalence relation. Okay, so whenever these three properties are satisfied, the given relation, that is called as the equivalence relation. The three properties are reflexive, symmetric, and transitive. Okay. See, for example, capital R equal to 1, 1, 1, 2, 2, 1, 2, 2, 3, 4, 4, 3, 3, 3, 4, 4. So now we can show the given relation is equivalence or not. See, the given relation is equivalence or not, thus it will be satisfy the three properties, that is the reflexive, symmetric, transitive. So the property of reflexive is x comma x belongs to R, symmetric is x comma y belongs to R, then y comma x belongs to R. Next, transitive, x comma y belongs to R, y comma z belongs to R, then x belongs to z is a transitive. So now I have to check. It is a reflexive since the relation 1, 1, 2, 2, 3, 3, 4, 4. Though it is a reflexive. Then symmetric 1, 2, 2, 1, 3, 4, 4, 3, 2, 1, 1, 2. So then it is called as a symmetric. Then transitive 1, 1, 1, 2, 1, 2, 1, 2, 2, 1, 1, 1, 1, 2, 2, 2, 1, 2, 3, 4, 4, 3, 3, 3, 4, 3, 3, 4, 4, 4, 3, 3, 3, 4, 3, 4, 2, 1, 1, 1, 2, 1, 2, 1, 1, 2, 2, 2, 2, 2, 2, 1, 2, 1, 3, 4, 4, 4, 3, 4, 4, 3, 3, 3, 4, 3, 4, 4, 4, 3, 4. So these are the combinations of x comma y, y comma z, that implies x comma z. So now transitive is also satisfied. Therefore, capital R satisfies the reflexive, symmetric, and transitive. Then capital R is an equivalence relation. So the given relation is equivalence relation, then it will be satisfy the three properties. These are the reflexive, symmetric, and transitive. Okay, then we can say that the given relation is called an equivalence relation. Okay. Next, partial order relation. See, a relation R on set A is called partial order if R is reflexive, antisymmetric, and transitive. Okay, the given relation R is partial order of if R, then it will satisfy the three properties. The first one is reflexive, second one is antisymmetric, third one is transitive. Okay, see, let A equal to 1, 2, 3, R equal to 1, 1, 2, 2, 2, 3. So it is also reflexive. Then A comma B belongs to R, then B comma A does not belongs to R. So it is antisymmetric for A comma B and B comma A. It is transitive for every A comma B, B comma C. It does not exist. There is no need to choose. So since if it is reflexive, antisymmetric, and transitive, though the given relation is a partial order relation. Okay, so equivalence relation means it will satisfy reflexive, symmetric, transitive. If it is partial order relation, then it will satisfy reflexive, antisymmetric, and transitive. Okay. Next, Hussey diagram, that is the graphical representation of partial order relation in which allows heads are understood to be finding upwards is called Hussey diagram or poset diagram. So the graphical representation of a partial order relation in which all arrows heads are understood to be finding upwards is called a Hussey diagram or poset diagram. Okay. See, next procedure to draw Hussey diagram. First, we have to construct the diagram for the given partial order relation. Whenever the relation is given, we have to draw the diagram. Since the relation is reflexive, then eliminate the self loops. So, in the given relation is reflexive is there, that the reflexive of the self loops are eliminated. Next, since the relation is transitive, to eliminate the transitive edges, so the given relation is transitive, then we have to eliminate the transitive edges. Okay, if it is reflexive, we can remove self edges. If it is transitive, we can remove transitive edges. Okay. Next, eliminate arrowheads. Then after we can eliminate the arrows. Okay, arrowheads are eliminated. See, let x equal to set 2, 3, 6, 12, 24, 36 and less than or equal to be the relation such that x is related to y. If x divides y, draw the Hussey diagram of x, less than or equal to. Okay, so how to draw this relation? See, first of all, the given x equal to 2, 3, 6, 12, 24, 36. In that process, first of all, we have to draw the relation. The relation is less than or equal to, and it will be divides by, that is 2, 6, 2, 12, 2, 24, 2, 36, 3, 3, 3, 6, 3, 12, 3, 24, 3, 36, 6, 6, 6, 12, 6, 24, 6, 36, 12, 12, 12, 24, 12, 36, 24, 24, 36, 36. So likewise we have to draw the relation. Okay, so now how to construct this 2, 3, this is a 2, this is a 3. So 2, 3, 6, 12, 24, 36. Okay. See, 2, 2, 2, 6, 2, 12, 2, 24, 2, 36, 3, 3, 3, 6, 3, 12, 3, 24, 3, 36, 6, 6, 6, 12, 6, 24, 6, 36, 12, 12, 12, 24, 12, 36, 24, 24, 36. So, how the relation x divides y and x less than or equal to, see, 2, 2 divides and 2 less than or equal to 2. 2, 6 divides 2 less than or equal to 6. So, likewise we have to, first of all we have to write the relation, then after we go for the Hussey diagram. Okay. See, since reflexive remove all the loops. So reflexive 2, 2 removed, 3, 3, 6, 6, 12, 12, 24, 24, 36, 36 will be removed. Then remove the transitives 2, 6, 2, 2, then remove the 2, 6. Likewise, we have to remove all the loops. 2, 2 removed and 2, 6 will be available. 3, 3, 3, 6, 3, 3 removed, 3, 6 available. Okay, and remove all the arrows, then we get the Hussey diagram. Poset means rat. See, let A equal to 2, 4, 8, 16, 32 and less than or equal to be the relation. If of divisibility, A, B divisibility, draw the Hussey diagram. That is 2, 4, 2, 8, 2, 16, 2, 32, 4, 8, 4, 16, 4, 32, 8, 16, 8, 32, 16, 32. Okay, now. So likewise, we have to, first of all, we have to write the relation, then after go for the Hasse diagram. See, 2, 4, 8, 16, 30. So 2, 4, 2, 8, 4, 16, 8, 16, 16, 32. So this is a relation. You have to draw the Hasse diagrams. Okay. Next one. Let A be the set of divisors of 32 ordered by divisibility. So those are the divisors of 32. First of all, we have to write that one. That is, 1 is divisor of 32, 2, 4, 8, 16, 32. Okay, likewise we have to draw 1, 2, 4, 8, 16, 32. Okay. See next, in the functions, some of the problems, f of x equal to x plus 2, g of x equal to x minus 2, h of x equal to 3x, then find g circle f circle g circle g, h circle g circle f. Okay, see, g circle, that is g of f of x, that is f of x is the x plus 2, then it is a call is g of x, that is in the x place we have to write x minus 2, that is x plus 2 minus 2, that equal to x. Okay, so likewise we have to draw the from circles, that is the compositions, that is g circle f of x, f circle g of x, g circle of h circle g, h circle f, h circle g circle f. See, h circle h of g of f of x, h of g of x plus 2, g of f, that is x minus 2 plus 2, that is x, h of x equal to 3x. So likewise we have to draw the compositions. Same draw, just g circle f circle g, f circle f of x, g circle g of x. Okay. Next, definition of lattice. A lattice is a poset in which each pair of the elements has least upper bound and greatest lower bound. That is called as a lattice. A lattice is a, simply we can say, is a poset in which each pair of the elements has least upper bound and greatest lower bound. That is called as a lattice. Or a poset is called a lattice if it is both meet semi-lattice or join semi-lattice. Okay, a poset is called a lattice if it is both meet semi-lattice and join semi-lattice. Okay, meet is denoted by V, greatest lower bound, and join is denoted by and least upper bound. So meet is denoted by or symbol and join is denoted by and symbol. That is called as the greatest lower bound, that is GLB. It is join is called least upper bound, that is LUB. Okay. So lattice is a poset in which each pair of the elements has least upper bound and greatest lower bound, or it is called as the meet semi-lattice or join semi-lattice. Okay. Minimum number or lower bound. See, let p comma less than or equal to is a poset and element y belongs to is called a minimal number of p if for all x belongs to p comma y less than x, then it is called as minimum number or lower bound. And a maximum number or upper bound, p comma less than or equal to is a poset and element y belongs to p is called a maximal number of p, that is if for all x belongs to p comma y greater than x, that is called as a maximal number or upper bound. See, for example, A, B, C, D. So least upper bound is, it is called as a D, and greatest lower bound is A. Okay, here least upper bound is A and here greatest lower bound is 5. So likewise we have to assign the minimal and maximal values from the lattices. Next, Boolean algebra and Boolean functions. See, a complemented and distributive lattices, that is into comma not comma 0 comma 1 is called a Boolean algebra. For example, B equal to set 0 comma 1 is a Boolean algebra. Here we consider into and NOR or binary operations on B. That is, it consists of greatest lower bound of 0 and least upper bound of 1. That is called as the Boolean algebra. See here, in the Boolean object, different type of properties are there. The first one is the idempotent law. That is A into A equal to A nor equal to A. And the commutative law, AB equal to BA, A nor B equal to B nor A. Then associative, A into B into C equal to A into B into C. And absorption law, into of A nor C into of A nor B equal to A, or A of A into B equal to A. And distributive law, A into B nor C equal to A into B nor C, and A nor B into C equal to A nor B into C. Okay. So these are the properties of Boolean algebra. That is idempotent law, commutative law, associative law, absorption law, and distributive law. Okay. In Boolean expression, a Boolean expression in variables x1 comma x2 comma x3 and so on xn is any finite string of symbols formed in the following rules. So it will be follow the different rules. First one is 0 and 1 are Boolean expressions. X1 to xn are Boolean expressions. If alpha and alpha 2 are Boolean expressions, then alpha 1 product of alpha 2 and alpha 1 sum of alpha 2 are also Boolean expressions. Okay. Next, recurrence relation. In other words, a recurrence relation is like a recursively defined sequence but without specifying any initial values, that is the initial conditions. Therefore, the same recurrence relation can have the multiple solutions. If both the initial conditions and the recurrence relations are specified, then the sequence is uniquely determined. So for example, consider an equal to 2 an minus 1 minus an minus 2 for n equal to 2 comma 3 comma 4 and so on is the sequence of an with an equal to 3 and a solution for this recurrence relation. For n greater than or equal to 2, we see that 2 an minus 1 an minus 2 equal to 2 of 3 of n minus 1 minus 3 of n minus 2 equal to 3n, that equal to an. Therefore, an with an equal to 3 is a solution of the particular recurrence relation. Okay. Next, is the sequence of an with an equal to 5 a solution for the same recurrence relation C? For n greater than or equal to 2a n minus 1 minus n minus equal to 2 into 5 minus 5 equal to 5, that equal to an. So therefore, an with n equal to 5 is also a solution of the recurrence relation. Next, least upper and greatest lower bounds. So a least upper bound, that is LUB of two elements x and y, is a minimal element in the intersection of the upper bounds of x and y. These are the intersection of the upper bounds. And here greatest lower bound is the maximum element in the intersection of the lower bounds of the x and y. So intersection of the upper bounds are the least upper bound. Intersection of the lower bounds are the greatest lower bounds from the x and y. Okay. Next, algebraic structure. See, these are the introduction is binary operations, definition of groups, examples of groups, and subgroups. Okay. So binary operations. A binary operation on a set is a rule for combining the two elements of the set, that is called as a binary operation. See, let S be a non-empty set and product be any operation defined in S, then product is said to be binary operation on S. That is, see, if for all A comma B belongs to S, that implies A product B belongs to S. That is, whenever we have to combine the two elements based upon the sets, then it is called as a binary operation into plus. These are the binary operations. So a binary operation on a set is a rule for combining two elements of the set. Let S be a non-empty set and product be any operation defined in S, then product is said to be binary operation on S. Then for all A comma B belongs to S, that implies A into B belongs to S. See next. Let n equal to set 1, 2, 3, 4, set of all natural numbers for all A comma B belongs to n, that implies A plus B belongs to n. For all A comma B, this is a 1, 2 belongs to n, that implies 1 plus 2 equal to 3 belongs to n. So natural numbers are 1, 2, 3, 4 and so on. Whenever you go for the plus, that is a binary operation or not. So for example, A comma B belongs to n, that is A plus B belongs to n. So we have to take the values of A comma B values, that is 1, 2. That is, the condition is A plus B, then 1 plus P, 1 plus 2 equal to 3, that is belongs to n. Therefore, plus is a binary operation in n, that is a natural numbers. Therefore, n comma plus is always a binary operation. For all 1, 2 belongs to n, that implies 1 minus n does not belongs to n. Only addition operation is the n plus is a binary operation. Whenever you get taken the subtraction, it is not a binary because of minus 1 does not belongs to the natural numbers, that is n. Next, properties of binary operation. See, let product be a binary operation on non-empty set S, then product is said to be, it is a closure property, associative property, identity property. See, in the closure property, for all A comma B belongs to S, then A product B belongs to S. In associative property, for all A comma B comma C belongs to S, that is A product B product C equal to A product B product C. Then identity property, there is an identity element belongs to S such that E product A equal to AE equal to A. Then for all A belongs to S, that is AE equal to EA equal to A. Then it is called as an identity property of the binary operation. Next, commutative property, that is for all A comma B belongs to S, then A product B equal to B product A belongs to S, that is called as the commutative property. Next, algebraic structure or algebraic system. See, any non-empty set equipped with one or more binary operations is called an algebraic structure or algebraic system. For example, set of natural numbers n comma plus comma into is an algebraic system. Set of integer, that is z comma plus comma minus comma into is an algebraic system. Okay, see, natural numbers, that is n plus comma into, integer, that is z comma plus comma minus comma into, these are the algebraic structures. Next, algebraic structure or algebraic system, that is an algebraic system S comma product is said to be groupoid, semigroup, monoid, that is group. See, groupoid if satisfies the closure, and semigroup if satisfy the closure and associative, monoid if satisfy the closure, associative and identity, then group is these three are satisfied, then it is called as a group. Okay, if it is a groupoid, it satisfies the closure operation like closure maximum. Semigroup, it satisfies closure and associative. It is a monoid, it satisfies closure, associative and identity. Then group, if it all satisfies, that is a group, semigroup, monoid, that is called as a group. Okay, so algebraic like group satisfy equivalent, it may be closure, closure associative, closer associate int, then it is called as a group. Okay. Next, abelian group. So what is meant by an abelian group? Abelian group is if it satisfies closure, associative, identity, inverse and commutative properties, then the given group is called an abelian group. If it satisfies closure, associative, identity, inverse and commutative, then it is called as abelian group. Okay. So properties, if A comma B and C are elements of a group G, then A inverse whole inverse equal to A, AB whole inverse equal to B inverse, A inverse, AB equal to AC or BA equal to CA implies that B equal to C. That is the, it will be perform the cancellation law. In cancellation, left cancellation law available, right cancellation available. So based upon condition we have to use the left or right. Okay, these are the properties. A inverse whole inverse equal to A, AB whole inverse equal to B inverse A inverse, AB equal to AC or BA equal to CA, that implies B equal to C, using for the cancellation law like left cancellation or right cancellations. Okay. Next one, subgroups. In subgroups, it often happens that some subset of a group will also form a group under the same operation, such that a group is called a subgroup. That is, if G comma star is a group and H is non-empty subset of G, then H comma star is called subset of G or subgroup of G comma into if the following conditions hold. A into B belongs to H for all A B belongs to H is a closure relation. Simply we can say that subset of group is called a subgroup. Simply we can say that subset of a group is called a subgroup. Subset of a group is called a subgroup. See definition. Let G be a finite group, that A belongs to G, then the order of A is called a number of elements in A, that is called as a product. Then definition, if G is a finite group, then the number of elements in G is denoted by module G is called as order of G. It is called as order. That is, if G is a finite group, then the number of elements in G is denoted by G is called the order of G. Next, normal subgroups and quotient groups. Okay. Coset. Let capital G be a group and H be a subgroup, then for A belongs to G, then HA equal to HA is such that H belongs to H is called right coset of H in G, then AH equal to AH is subset H belongs to H is called a left coset of H in G. These are called as the coset. HA equal to HA such that H belongs to H, AH equal to AH such that H belongs to H is called as the right coset of H in G and left coset of H in G. Okay. Next one. Next one. Normal subgroups and quotient groups. See, normal subgroup. A subgroup H of G is called a normal subgroup if for any A belongs to G, that is AH equal to HA, that is left and right cosets are same, then is called a normal subgroup. That is, the left coset group and right cosets are same, that is called as a normal subgroup. Next, homomorphism. See, definition of homomorphism: if G comma dot and H comma product are two graphs, then FG to H is called a group of homomorphism if f a into b equal to f of a is product f of b for all a comma b belongs to G. We often use the notation f g comma dot, that is h comma product, for such homomorphism. Many authors use the morphism instead of homomorphism. So morphism it is instead of the homomorphism. So what is the homomorphism? G comma dot and h comma product are two groups. The function f g to h is called a group of homomorphism, that is f a dot b equal to f of a product f of b for all a comma b belongs to G, that is called as a homomorphism. Many authors use the morphism instead of the homomorphism. Okay. See example of homomorphism. For example, the function f z to zn is defined by f of x equal to x is the group of homomorphism. Let p the group of all real numbers with operation addition, and let p plus be the group of all positive real numbers with operation of the function. The function fp equal to is defined by f of x equal to u power x is the homomorphism for if x comma y belongs to p, then x plus y equal to e power x plus y is equal to e power x plus e power y. That is called as the homomorphism of the particular function. See theorem. Let f g to h be a group of morphism, and let each g and eh be the identities of g and h respectively. Then f of eg equal to eh, f of a inverse equal to f of a minus 1 for all a belongs to G. That is, since is a homomorphism, f eg of f equal to f of eg equal to f of eg equal to f of eg eh. Hence it follows by the cancellation h. F of a inverse equal to f of a inverse equal to f of eg, that is equal to eh by 1. Hence f of a inverse is the unique inverse of the given group. See, if f g to h is a group of morphism, then the kernel of f denoted by kerf. So here we can assign kerf is the kernel of f is defined by the set of elements G that are mapped by f to the identifier of h, that is ker f equal to G belongs to G such that f of G equal to eh. That is called as the ker of the given homomorphism. That is ker f equal to G belongs to capital G such that f of G equal to eh. And the proposition let f g to h be a group of morphism, then ker f is a normal subgroup of G, and if it is injective, if and only if the ker f is a subgroup of f of h. Okay. Next, the pigeon hole principle. Suppose m pigeons occupy n pigeon holes, and if m greater than n, then 2 or more pigeons occupy the same pigeon hole. If there are more pigeons than the pigeon holes, then there must be at least one pigeon hole that has more than one pigeon on it. That is, if k plus 1 or more objects are placed into k boxes, then there is at least one box containing 2 or more the objects. Okay, it is called as the pigeon principle. That is, if there are more pigeons than the pigeon holes, then there must be at least one pigeon hole that has more than one pigeon on it. That is called as the pigeon principle. Pigeon hole principle. See, if k plus 1 or more objects are placed to k boxes, then there is at least one box containing the 2 or more objects. Okay. See, for example, if 6 pigeons occupy 4 pigeon holes, then at least one pigeon hole must contain 2 holes. See, find the minimum number of students of a class, and students were born the same month and date. See, same month equal to, that is a 12, then each one is occupy one space, that is equal to 12 plus 1 13 students. Same date 365, then 360 plus 1 equal to 366 students. Okay, so likewise we have to construct the pigeon principles. Okay. Okay, next.